Okay, today we're going to finish Chapter 5 on thermochemistry and talk about how we actually calculate our delta H's for our reaction. So last time we had our thermochemical equations, which was our reaction, and then it told us how much heat it either gave off or it took in. So we're going to learn how to calculate that value today. We can do it in a couple different ways. So first we're going to talk about heat capacity. So heat capacity is the amount of heat required to raise the temperature of a substance by 1 degree Kelvin or 1 degree Celsius. And the greater that heat capacity is for a substance, the greater the amount of heat you have to add to get it to increase its temperature. So something with a very large heat capacity, you have to add a lot more heat or energy to change its temperature by 1 degree. Something with a lower heat capacity, it's going to take a little less energy to do that. So let's look at the example. Of the following substance, which would experience a greater change in the temperature when the same amount of heat is added to each? So we have water, which has a C of 4.184, nitrogen gas, which has a value of 1.04, and iron, which has a value of 0.45. So out of these three, the answer should be C, iron, because it has the lowest value. So it's going to have the largest change in temperature. Water has a very high heat capacity, and so it doesn't change its temperature very easily. So a lot of times in the winter, it's a little bit warmer by the water, or in the summer, it's a little bit cooler by the water, because water doesn't like to change its temperature very efficiently or very well. So we can actually calculate using that heat capacity. And our equation here for that is Q equals mc delta T. So MCAT, we used this last year in chemistry. So Q stands for the heat, and it's measured in joules. So how much heat you have to give in or take off in the reaction. M stands for mass, measured in grams. C is just a specific heat, so same as saying heat capacity, a lot of times they're used interchangeably. So that is measured in joules per gram degree Celsius, or if you look down here in the table, joules per gram Kelvin. Same thing, you don't have to convert the number or anything to get the temperature to change like that, or unit to change. And then delta T, remember delta, wherever we see delta in a reaction, that means change in. So our change in temperature, final minus initial. Now these C's, or specific heats for different substances, are given in your textbook. If you look on page 182. If you were taking a test or something, or on the AP test, they would give you a table like this so that you could find those values within the problem. So let's try an example problem. So how much heat is required to warm 250 grams of water from 22 degrees Celsius to 98? And then it wants us to convert that heat capacity for water into a molar heat capacity. So we're going to be using our equation, Q equals mc delta T. And we're asked to solve for how much heat. So that would be Q that we're trying to find. So our mass of our water is 250 grams, so that is the right unit. C, if we look back on that table on the previous slide, or look in your textbook on page 182, we get 4.18 for water's heat capacity, joules per gram degrees Celsius. And then our temperature change, final minus initial, so 98 minus 22 degrees C. So we're going to solve for Q to get our answer. So 250 times 4.18 times our difference in temperature, 98 minus 22. And we get a Q of 79,420. And our unit, let's look. So grams and grams cancel. Celsius and Celsius cancel. One on top, one on bottom for each. So that means we're left with joules. Now we want to round our number to the correct number of significant figures. So it looks like 2 for our problem here. So our answer should be 79,000 joules. So now we want to convert our heat capacity, so that would be our C, 4.18 joules per gram degree Celsius, into a molar heat capacity. So molar just means instead of in terms of grams, we have it in terms of moles. So we have to convert our grams into moles by doing a mole conversion. So grams to moles, we use our molar mass. So our 1 mole is going to go on bottom. Grams have to go on top, so they cancel with grams on the bottom. We want to calculate the molar mass of water. So 2 hydrogen, 1 oxygen, you get 18.016. So we're going to multiply the two together to get our answer. So 4.18 times 18.016. And we're going to get a molar heat capacity of 75.3 joules per mole this time, degrees Celsius. Okay, so those would be the two answers to that problem. So next let's talk about the actual technique that we use to measure our Q or our delta H. So we use a technique called calorimetry. So we can't measure the enthalpy change of our reactants and products. We have to actually use the technique called calorimetry to get our delta H. So a lot of times when we're talking about calculating delta H, we use the technique calorimetry to do that. So it's going to measure the heat flow, so the flow of the heat from our reactant and products, so from our reaction, to a solution in the calorimeter. So on the left here we have a coffee cup calorimeter, which is a technique that we would probably use in lab. So we have an insulating cups that will keep the most of the heat in as possible. We have our reactants there in the solution, and so we would measure the change of when we add the reactants to how much the temperature changes of the water. A more scientific instrument is called a bomb calorimeter, which is shown here on the right, but it does the same thing, just a little bit better. So when we're using the calorimeter, we're using this relationship. So for an exothermic reaction, our solution, whatever we have it for the contents in our cup, the liquid part, is going to be gaining the heat. And the reaction part, our reactant and products reacting, are going to be losing the heat. For an endothermic reaction, our reaction is going to be gaining the heat and our solution is going to be losing the heat. Go ahead and try an example problem. So when a student mixes 50 milliliters of hydrochloric acid with 50 milliliters of sodium hydroxide in a coffee cup calorimeter, the temperature changes from 21 to 27.5. We want to calculate the change in enthalpy for the reaction in kilojoules per mole. So whenever we find Q for our reaction, okay, that's going to be a lot of times equal to our delta H for our reaction. Okay, we just have to maybe do a little bit of a unit conversion, because remember Q is going to be measured in joules per some gram, and our delta H we want to be measured in kilojoules this time per mole. But we're going to be solving for our reaction change. And if we notice, the relationship is our solution is going to be gaining the heat, and our reaction is going to be losing the heat. Okay, but we have all the values for our solution, for Q. So Q, remember, equals mc delta T. So we're going to use that relationship. So the mass of our solution times the specific heat of our solution times the temperature change of our solution equals negative Q of our reaction. So the mass, we can assume we have a total volume of 100 milliliters, and the density of that solution is 1. So if we have 100 milliliters, and we know its density is 1 gram per 1 milliliter, that means we would have 100 grams of our solution. So for M, we're going to plug in 100. Tells us our specific heat is 4.18. And our temperature change was from 27.5 to 21. And that equals negative Q for our reaction. So to solve, we're going to take 100 times 4.18 times our temperature change, 27.5 minus 21. And we get an answer of 2,000 717 joules. But that equals negative Q of our reaction. So we just want the Q for our reaction. So to get rid of the negative, we would divide by our negative. So we would get a negative number for our answer. Okay, so that gives us Q for our reaction. So at a constant temperature and pressure, or at a constant pressure, our delta H and our Q are going to be very similar. So we just got to convert our units from grams, joules per gram, to kilojoules per mole. So we're going to take the number we got, 2,717 joules per some mass of our reaction. And we're going to convert joules into kilojoules. So there are 1,000 joules, 1 kilojoule. And then we got to convert our grams, using our molar mass, into so many moles. Now to get our molar mass, we're going to use, or to get our moles of our hydrochloric acid solution, we're going to use the molarity that it gave us. So it gave us a molarity of 1. Remember that equals so many moles. And we used 50 milliliters, so that'd be 0.05 liters. So to get our mole conversion there, we would take 1 times 0.05. So we would have 0.05 grams of our solution. And so we're going to divide by that to get the unit of moles, because we want it in kilojoules per mole. So we're going to divide by that 0.05. Or, sorry, yeah, 0.05. So we're going to take 2,717 divided by 1,000 divided by 0.05. And we get an answer of 54.3 kilojoules per mole for our final answer. So let's move into now talking about Hess's law, or excuse me, talking about how another way we can find our delta H for a reaction. So there are two other ways we can find the delta H for our reaction. So if you remember, our thermochemical equation had the equation, and then it gave us a delta H for that reaction. So how do we actually calculate that delta H? So there's two methods we can use. So one is Hess's law, and Hess's law says that for a reaction, if it's carried out in a series of steps, the delta H for that overall reaction will be the sum of their individual delta H's for each of those individual steps. So that's one way we can find it. Another way is that we can calculate the enthalpy of formation using this equation here. So our delta H for our reaction would be the sum of the delta H's of formation of our products times by their coefficients minus the sum of the delta H's of formation of our reactants times their coefficients. Now the delta H of formation here with the little f, that's what it stands for. Those are just in a table in the back of your textbook. And so we're just going to sum up all of those, times them by their coefficients for each of those and subtract them. So our products minus the reactants. So let's talk about Hess's law first. So Hess's law is just the sum of a series of delta H's for each individual step in our reaction. So we will be given these delta H's for each part of our reaction. Now we can reverse them or multiply them by some coefficient, and we would do the same thing to the delta H's. So if our reaction is reversed, we would change the sign of delta H. If our reaction is multiplied by some coefficient, we would multiply that delta H. So let's try an example. So here we are given two steps for our reaction, and we want to get to this overall reaction number 3. So we look at our delta H's. So we have 1/4 P4 plus 3/2 of Cl2 giving us PCl3. So we see the P4 as our reactant, so we're not going to change that reaction. We're going to leave it how it is. Okay, and we're going to leave the delta H then how it is. So I'm going to rewrite that a little bit down below here. So 1/4 of P4 plus 3/2 of Cl2, giving us PCl3. And our delta H stays negative 319.7. Okay, now we look at the other equation, and we notice it doesn't really necessarily change as well. So we want the PCl5 to stay as a product. So I'm going to rewrite that. PCl3 plus chlorine gives us PCl5. And now I want to add these two reactants together. Remember, I'm trying to get this overall reaction here on top. So first I ask myself, is there anything I can cancel? So I can cancel the chlorine PCl3s. They appear on both sides. I can leave my 1/4. There's nothing I can cancel it with. I want to add these two fractions together. I'm going to rewrite it like this. So I get 3 plus 2 gives me 5/2 chlorines, and then PCl5. So I've rearranged my two given reactions to get my sum of my overall reaction. So this one was pretty easy. I didn't have to do anything to them. So to find my overall delta H for this reaction then, I'm just going to add up my two delta H's for the individual parts. So negative 319.7 plus negative 132.8. And I get an answer of negative 452.5 kilojoules. And so that would be my answer. Let's try another one that maybe is a little bit more difficult. So here I'm given 3 reactions that I have to rearrange to get this 4th overall reaction. So I'm going to start by looking at my first given reaction. Now if I notice, my C6H6 is on the wrong side. It needs to be a reactant down here, and right now it's a product. So I'm going to flip that reaction. So C6H6 goes into C6 plus 3H2s. Now because I flipped that reaction, I have to flip the sign of my delta H. So my delta H would now be negative 49.0. Okay, now I'm going to look at my next reaction. So for this one, what do I have similar? So maybe my CO2s are similar. So it should stay a product here, and it should stay a product here. But if I notice my carbon, okay, it needs to eventually go away. So right now I have 6 down here, but I only have 1 there. So they're not going to cancel. So I'm going to have to multiply this whole equation by 6. Okay, so that my carbons will eventually cancel, and then I'll have 6 CO2s. So I'm just going to multiply in by 6. So 6C plus 6O2 gives me 6CO2. So because I multiplied that reaction by 6, I now have to also multiply my delta H by 6. So negative 393.5, I need to times by 6 as well. Now my following reaction, I want to look at my waters. So water appears in both of them, but I need 3 waters. Right now I only have 1. So I'm going to have to multiply that whole reaction by 3 to get my waters to be correct. So 3H2 plus 3/2 oxygen will give me 3 H2Os. And so because I multiplied my delta H, my reaction by 3, I have to multiply my delta H by 3. Okay, so now let's see if we have our reaction correct. So can I cancel anything first? So I can cancel these, and I can cancel my hydrogens, which is good because they don't appear in my overall reaction. And so what am I left with? So I'm left with C6H6 plus, I'm going to add together all of these oxygens. So we have 6 plus 3 halves, so that would give us 15/2 O2 plus 6 HCO2s and 3 waters. So that matches. So now all I have to do is add together my delta H's, making sure I multiply them by the right numbers. So negative 49 plus negative 393.5 times 6 plus negative 285.8 times by 3. I'm going to get an answer of negative 3,267.4 kilojoules. So that's all Hess's law is. Okay, so on your homework today, you're going to have to do a couple more of these. So let's talk about the other way we can calculate delta H. Okay, so Hess's law, we use a series of steps to get our overall reaction. But what if we don't know what the steps are? So then we would use our enthalpy of formation. So a lot of our data, we have a lot of data on those delta H's for different reactants and products, not necessarily for the overall reaction. And so we're going to use this equation, our sum of our delta H's of formation of our products times by their coefficients, minus the sum of our delta H of formation of our reactants times their coefficients. So if we had this overall general reaction here, so here's our reactants, here's our products. So we had to take our products first. So the formation of C, substance C, times by its coefficient C, plus the other product, which is D, so the formation of D, times by its coefficient. So we want to add those together first, so make sure you put those in parentheses, or you find that number, and then we're going to subtract it from our reactants. So the delta H of formation of substance A times by its coefficient, plus the delta H of formation of substance B times its coefficient. So this all of these values are in Appendix C in your book. If you were doing this on a test again, they would give you a table of values to use. So let's find the delta H for this reaction. So we have CO2, H2O are our products, and we're going to subtract them from our reactants. So we're going to open up Appendix C in our textbook, and we're going to look for our reactants, or our products first. So I have to find Appendix C here, just give me a second. And so we want to look for CO2 and water. And it should have them kind of by what elements are in them. So CO2, and we want to make sure we chose the gas form of it. So CO2 gas has a delta H of formation of negative 393.5. We want to times it by its coefficient, so we're going to times it by 2. Plus, we're going to add it to water's value. So water, I think we put it with the oxygen. So water, and we want to make sure we use the gas form of water. And its coefficient is 4. So 4 times its delta H of formation, which is negative 241, sorry. 41.82. Okay, and we want to find the sum of that, so I'll put that in brackets. And we're going to subtract it from our reactants. So we want to look for methanol. times negative 201.2 plus oxygen, O2 gas, which is 0, easy one. Now I'm going to do each of these brackets first on their own, and then subtract them from one another. Just makes it easier and make sure you don't make any mistakes or miss a parentheses. So 2 times 393.5 plus 4 times negative 241.82. So I get negative 180. I think that was supposed to be a negative sign. 2 times negative 393 plus negative 4 times negative 241.82. So we should get negative 1,754.28. I'm going to subtract that from what I get down here. So 2 times negative 201.2. So I get negative 402.4. So minus a negative would be adding it. So 1,754.28 minus a negative 402.4. So I should get an answer of negative 1,351.88 joules. So my delta H for that reaction would be that value. Let's try one more. Okay, so here I have calculate the enthalpy change for the reaction using our enthalpies of formation. So I'm going to take my products over here minus my one reactant. So liquid water has a value of, let's see, negative 285.83. I'm going to times that by 2. I'm going to add it to oxygen, which we know is 0 from our last problem. Okay, and I'm going to subtract that from my reactant. So liquid water this time has a value of negative 2, not water, hydrogen peroxide. So liquid though, so negative 187.8. So I'm going to calculate each side individually and then subtract them from one another. So 2 times negative 285.83. So I get negative 571.66. I'm going to subtract that from 2 times 187, negative 187.8. So minus a negative 375.6. So negative 571.66 minus a negative 375.6. So I get a delta H for my reaction to equal negative 196.06 kilojoules. So this reaction, because we have a negative number, remember, means an exothermic reaction. So in homework today, you're going to have a couple different examples of each one of these problems.